Outer space. What is the temperature of outer space? What does temperature even mean in the outer space? Well, we know that the space is full of stars and planets, and we know how to measure temperature there. But what if we focus on a region that is empty? Well, those regions are not really empty. They're full of light. This light was emitted a very long time ago, at the beginning of the universe. It's called cosmic background radiation, and its average temperature is 2.7 Kelvin. But how do we measure the temperature of this radiation? Do we just put a thermometer and read it? No, it doesn't work like this. And also, what does temperature of light mean? Well, we have to consider two different kinds of light. The light emitted by our lamp in the house, is the incoherent light. While the light emitted, for example, by a laser, it's called coherent light. And these two kinds of lights are very different. So let's take a closer look. The coherent light, the one emitted by a laser, has always the same color and a very well-defined phase. While if we consider more closely the light that is emitted by our light bulb, we can see that it has a distribution of colors and phases. Again, this is the one that is called incoherent light, and this is the kind of light that we can use for measuring temperature, because the distribution of the light itself, the amount of color and different proportion between different photons, it gives us the temperature. So let's go back to the outer space now. If we check the distribution of these photons, we see that there are very little photons at high energy. Like, for example, if we check the blue photons, there is not even one. And the same is, for example, for the red photons. But if we consider the microwave photons, we see a lot of them. And this is because their average temperature of the cosmic background radiation is 2.7 Kelvin. But how low can we go? Can we measure 1 Kelvin, 0.1 Kelvin? Well, in our measurement, we managed to measure 37 millikelvin. And for doing that, we took an atom. But no, not like this, not a real atom. We build an artificial atoms. How do we build it? Well, it seems very strange, but these atoms are really simple to realize. They're just electric circuits made in aluminum. So what are the difference between the natural atom and the artificial one? Well, we all know the natural atoms. They come more or less in 100 flavors, and they are collected in the Mendeleev table. If we do experiment, each of these atoms have different properties, but we are stuck with that. We cannot create different properties of different atoms. With the artificial ones, instead, we can design their properties on multidimensional axes, so we can choose in a continuum of possibilities. And this is the strength of artificial atoms. But how do we build one? So, for people that studied a bit of electric circuits, these artificial atoms are just LC oscillator. We design this atom in aluminum, and for technical reason, we usually use big aluminum cross. And these cross are gonna get surrounded by a big metal plane that is called ground plane. We can associate the different parts of the LC circuit to the qubit or artificial atoms. The capacitance is given by the two electrodes, the cross and the ground plane, while the inductance is produced by a Josephson junction, two different pieces of superconductors that cross each other. How do we engineer the properties of these artificial atoms. The one that we described are called superconducting artificial atoms. They are electric circuits made of superconductors. So in order to change their properties, we just need to engineer their parameters. For example, just changing their dimensions, it will change capacitance and inductance. And these will reflect in changing the energy level structure. For example, increasing the capacitance in one circuit, it will give much smaller separation between their energy level. Now we have these atoms and we can engineer the level structure. But how do we exchange energy with the atom? How do we connect it with it? Well, it's very easy. We can just couple the external world to the atom with the capacitance. And in practice, we just draw a circuit that coupled to it. This circuit, this coupler, again, just a capacitance, is made of superconductor as well, aluminum in our case. And we can use this coupler to test and measure the qubits. And again, we can recognize all different parts of the qubit connected to the LC oscillator. So in particular, the capacitance is given by the different electrode, the cross, that is the qubit, and the ground plane, that is all the metal around. We have the inductance, this is a Josephson junction, and we have our capacitance that couple our circuit to the external world. And in particular, here is given by this C-shaped electrode. In the picture, you can see an actual artificial atom that we fabricated at Chalmers. This picture is taken with a microscope, but if you read the length scale on the bottom right, you see that it reads 100 micrometer. That is the thickness of a human hair. This means that these artificial atoms are macroscopic objects. In fact, we can look at it and see it by naked eyes. So now we have all elements for building our thermometer. But why these artificial atoms can be used as thermometer? So if we send a coherent tone, if we send a photon to an artificial atom, all the photon will come back. But if this atom is embedded in a radiation field, in some bath of photons with some energy distribution, with some temperature, then not all the incoming photon will get reflected back, just a small part. And this is the principle that we want to use for measuring temperature. In our experiment, we build a superconducting artificial atom and we put in the coldest place in the universe, a dilution refrigerator. We send a coherent tone and we read out whatever comes back, whatever is reflected by the atom. And in order to calibrate this thermometer, we inject together with the coherent tone some noise, some artificially induced temperature. And when we plot our result of the noise of the injecting temperature versus the reflection that we measure from the qubit, we see that our data are described by the theory very well. But what can we use this thermometer for? So many universities and industries are trying now to build a quantum computer with superconducting qubits. In order to control the quantum processor put at the lowest temperature stage of the dilution refrigerator, we needed to connect it with many lines. So our thermometer can assess the temperature of each of these lines. On top of that, Any quantum system at very low temperature, for example our qubit, is connected to different systems at different temperature, different thermal baths that compete in warm up or cool down our system. So with our temperature, for example, we can read flow of this energy. I hope I give you a lot of ideas and that you enjoyed this presentation. And if you are curious, I encourage you to check our publication on PRX about this thermometer and about our work that we do with superconducting qubit. And with this, I thank you for listening, and to the next video.